So I welcome boys and girls. In the previous video we have seen about defects, stoichiometric defects, about vacancy and interstitial defects in non-ionic compounds, and also we have seen about Frankel and Schottky defects, Schottky and Frankel defects. Do you remember that? Now there is a third variant in this, that is called as impurity defect. These impurity defects right now we examine. And impurity defects are generated by adding an impurity like Sr plus 2 in NaCl. Addition of each Sr plus 2 can generate one Na plus vacancy. Reason: Sr is having plus 2 charge, so it sits in the position of one Na plus, that triggers the vacancy in another Na plus position. Similarly, if I put Al plus 3 ion in NaCl can sit in one position of Na plus, and 1 Al plus 3 is equal to 3 Na plus, hence automatically 2 Na plus positions will become vacant. Such defects generated are called impurity defects. Very quickly we look at their diagrammatic representations right now for our clarity. Okay, are we ready? Now we see first what? First we see the vacancy defect. This is vacancy defect. In the equilibrium position, some particles are missing. Next, this is interstitial defect. In the position where we are supposed to have gaps, particles are sitting. Next, we see this is your Frankel defect. So whenever the cation is very small, cation, anion vary in their sizes greatly, cation from one of the positions will slip and sit in a void. This won't affect the density, but such defects are seen in AgCl, AgI, etc., where coordination number is less. These are seen in ionic compounds. This is a Schottky defect which we have seen. Equal number of cation anions would be missing from their places. So many such defects can decrease the density of crystal lattice. And we have seen next, if I am putting a Sr plus 2, this is called as a impurity defect. 1 Sr plus 2 is equal to 2 Na plus. So if I am putting 1 Sr plus 2 in the position of 1 Na plus, automatically it is triggering vacancy here. Can you see that? This is vacancy created by this. Similarly, if I put Al plus 2 here, it can generate two such vacancies. If I put 2 moles of Sr plus 2 in 100 moles of salt, I will get 2 moles of defects, vacancies. Now the third variety which we want to discuss here is the non-stoichiometric defects. These defects will result in the formation of compounds which don't fix up to any particular formula. Now we see first metal excess defect. If I am putting some NaCl and Na vapor, the Na vapor will try to imitate the NaCl. It tries to, Na plus tries to generate itself by losing an electron. The electron will take the position of a particular anion. The presence of this free electron in the position of Cl minus ion can generate a particular characteristic yellow color. The center which can cause color to a crystal lattice is called F center, because F means Faber. Faber in German means color. Similarly, if I put NaCl in Na vapors, I get yellow color. The yellow color is due to the free electron. Similarly, KCl when heated with potassium vapors will give me the lilac color or some violet color. When lithium chloride is added with lithium vapor, I will be getting some pink color. All these are called as metal excess defects. Similarly, if zinc oxide is heated, this is also a metal excess defect, but this is happening due to heating of zinc oxide, as zinc oxide is losing electron and oxygen due to reversible loss of oxygen. These free electrons would take the position of oxide ion in the crystal lattice. The free electrons can undergo excitation and de-excitation that can impart yellow color to hot zinc oxide. When zinc oxide is cooled, it would take back the oxygen, it come back to normal white color. In the next video, we talk about metal deficiency defects in wostite and a numerical problem therein. Thank you.